This video is going to talk about Lewis structures, which is a method that chemists use to depict covalently bonded molecules. We do this using dots. So one dot represents one electron, and when atoms share two electrons, they form a bond, which we often represent instead of dots as a single line. Part of the reason why we do this is because drawing these Lewis structures lets us predict the three-dimensional shapes of these molecules. This is done using VSEPR theory, and we're not going to cover it in this video, but it is something that you're going to be applying Lewis structures to later on. Atoms can also share more than two electrons, and if they do, they can form different types of bonds. So if they share four electrons, like in this molecule here, they form a double bond. And this can be drawn as sharing two lines between them. And once again, we can use our Lewis structure to predict what they're going to look like in 3 dimensions. Likewise, if two atoms share 6 electrons, that's when they would form a triple bond. So they can share up to 6, while quadruple bonds are technically possible, where you would be sharing 8 electrons. This is not something you're going to ever have to see in a first-year chemistry course. Most elements also follow something called the octet rule, which means they prefer to have exactly 8 valence electrons. So for example, in these two molecules, we can see that carbon, in both cases, has 8 electrons. It's also important to remember that there will sometimes be electrons that are not represented as bonds. So you can see on the oxygen that 4 of the electrons are represented as unbonded. These are referred to as lone pair electrons. So 4 of oxygen's electrons are lone pairs, and 4 of oxygen's electrons are in bonds. And it still adds up to 8 electrons total. Hydrogen can only have up to 2 valence electrons, however. If we look at hydrogen on the left molecule, you can see that each hydrogen has 1 bond and no lone pairs, which means it only has 2 electrons. This is because it has a very small valence shell and cannot accommodate more than 2. Now let's go over an example of how to come up with these Lewis structures, because we need to have a strategy for tackling them. So let's use HCN as an example, and we're going to have a series of steps that we can follow for any Lewis structure we want to draw. The first step is to determine the central atom. So a tip is that the central atom will be the least electronegative atom. We need to remember what electronegativity means. If we look at the periodic table, it's generally sorted by electronegativity. So as we go up and to the right on the periodic table, elements become more electronegative. So if we want to compare hydrogen, carbon, and nitrogen, what we can see is that nitrogen is more electronegative than carbon and hydrogen. Nitrogen will not be the central atom. For HCN, carbon will be our central atom. Even though hydrogen is a little bit less electronegative than carbon, we have to remember that hydrogen can only form 1 bond. So it is not possible for hydrogen to be the central atom, because that would force it to form a bond with both carbon and nitrogen. That would be more than 2 electrons on hydrogen. The second step is we're going to place the other elements around the central atom. We decided that carbon was the central atom, so hydrogen and nitrogen can get placed next to the carbon. Next, we want to draw a single bond between the central atom and every outer atom. So we're going to draw a single bond between carbon and hydrogen and between carbon and nitrogen. We may end up making changes to this later if we decide we need double or triple bonds, but for now, we know that at the very least, there needs to be at least 1 bond connecting the atoms together. The next step is we're going to complete the octets on all the outer atoms by adding lone pairs. That means nitrogen needs to gain 3 lone pairs in order to have 8 electrons. However, hydrogen is a special case. Remember, it can only hold 2 electrons, so we do not need to complete the octet on hydrogen. Next, we want to complete the octet on carbon. But first, let's double check to see how many electrons we have left to use. Because every time we draw a Lewis structure, we have a maximum number of electrons that can get used in our structure. So how do we count this? What we're going to do is we're going to look at the periodic table. So the group number, which is the column number, is going to tell us how many valence electrons each element has. Nitrogen is in group 15, so it contributes 5 valence electrons. Meanwhile, carbon will contribute 4 because it is in group 14, and hydrogen will contribute 1 because it's in group 1. So if we add these all together, that equals 10 valence electrons total. So we want to compare this with how many electrons we have already drawn on our molecule. Currently, our molecule has 4 electrons in bonds and 6 electrons in lone pairs. We do not have any electrons left to use. If we had them, we would put them on the central atom. Because we have used the exact number of electrons, we're going to skip to the next step. Because the central atom still has an incomplete octet, we need to give it more electrons. But since we have already used all 10 electrons available to us, the only way to do this is to form double or triple bonds. We can do that by moving lone pair electrons into bonds like this. We can take those 2 electrons to form a double bond between carbon and nitrogen. Now carbon has 6 electrons in bonds, so we need to do this one more time. Those 2 electrons are getting moved into a bond, and then that is going to form our molecule. So now carbon and nitrogen both have 8 electrons. Hydrogen has 2 electrons, and we've used all 10 electrons that we were allowed to use. So the last step is we are going to check the formal charges on each atom. Formal charge is calculated in a fairly simple way. The equation is that formal charge equals the valence electrons minus the number of lone pair electrons minus the number of bonds. So each atom will have its own formal charge. Ideally, these charges will be as close to 0 as possible. Anytime you have a charge that is bigger than plus or minus 1, that is a problem and we need to fix our structure. So let's calculate the formal charge on hydrogen. Remember that because hydrogen was in group 1, it has 1 valence electron. Because it has no dots, it has 0 lone pair electrons. And because it has 1 line, it has 1 bond. So if we put these into the formula, we end up with a formal charge of 0 on hydrogen. For carbon, it is in group 14, so it has 4 valence electrons. It has 0 lone pair electrons because it has 0 dots, and it has 4 bonds. So this works out to be a formal charge of 0 as well. And finally, we have nitrogen. Nitrogen is in group 15, so it has 5 valence electrons. Then we subtract 2 from the number of lone pair electrons. There are 2 dots, so we subtract 2. And then we subtract 3 because nitrogen has 3 bonds, and that also equals 0. The fact that the formal charges all work out to be 0 tells us that this is a very reasonable Lewis structure to have drawn for this molecule. And that helps us confirm that this is the correct structure. If you see formal charges that are wildly different, that's when you know you probably have a problem. If you have formal charges that are +2 or -2, that is something that we try to avoid. In my follow-up video, we're going to do another example of working through how to draw a Lewis structure for a different molecule.